Hi guys, today we'll understand the geometric aspect of addition and subtraction of complex numbers. So basic algebraic aspect, we've seen that if I have a complex number which is a plus ib and a complex number z2, I'll say a1 b1 and a2 plus ib2. So if I'm adding the complex numbers, it simply means the real part is a1 plus a2 and the imaginary part is b1 plus d2. So this is regarding the algebra. Now the thing is, how do I visualize the complex number, which is the addition of two complex numbers? So for that, one thing which you have to understand is that complex numbers behave like vectors in the Argand's plane. In the Argand's plane. Vectors in Argand's plane. So if I have to add two complex numbers, I'll follow the law of vector addition here. Argand's plane. So if I have two complex numbers z1 and z2, so if this is z1 complex number and this is z2 complex number. So the triangle law says that if I have to add two vectors, the vector addition is nothing but if I have vectors or complex numbers z1 and z2, the new complex number, which is the addition, starts from the tail of z1 and ends at the head of z2, something like this. Okay, and in addition, in fact, the order also doesn't matter. If this is z2 and this is z1, the same rule follows. So what I have to do is I have to align the two vectors z1 and z2 in such a manner and then connect the tail with the head of the second vector or the complex number. So here if I follow something like that, this is basically z2, same magnitude, same modulus and same argument, and then the addition can be represented by a complex number like this. So the red one is z1 plus z2. This is how you add two complex numbers in the Argand's plane. If I have to subtract two complex numbers, for example, if I have to find z1 minus z2 in the same case. So what I'll do is, if this is z2 and this is z1, so minus z2 will be a complex number which points in the opposite direction, completely opposite direction with the same modulus. So this is minus z2. So now z1 minus z2 basically means z1 added to minus z2. Now what I have to do is I have to carry out the addition operation for z1 and minus z2. So this is minus z2. I'll just draw it here. And then I'll connect the tail with the head like this. So this is my complex number z1 minus z2. Complex number subtraction can be interpreted in a much simpler manner as well. So if I have a complex number z2 and z1, and if I have to represent the complex number z2 minus z1, so it's basically the complex number right in between the two. It starts at z1 and ends at z2, like this. So the dotted complex number is the z2 minus z1 complex number. We are doing this kind of interpretation because sometimes in questions it's much easier to understand z2 minus z1 in such a manner. Okay, so now we'll solve the last two questions from the previous complex number video using the geometric interpretation. Yeah. So the first A part is complex number z satisfies the equation argument of z plus 1 is pi by 6, z minus 1 is 2 pi by 3. Show that z is half times 1 plus root 3i. Okay, so firstly what I'll do is I'll represent the two complex numbers 1 and minus 1 on the Argand's plane. So 1 is a complex number which has a positive real part and imaginary part as 0. So it lies towards the right like this on the positive real axis. And minus 1 lies right opposite to it. This is minus 1. And z, since I have to show z is a complex number in the first quadrant, I'll assume z is pointing somewhere here like this. So now z minus 1. So z minus 1 is a complex number right in between z and 1, which starts at 1 and ends at z like this. So this complex number is z minus 1. And z plus 1 is basically the difference between z and minus 1. So I can represent it like this. So this is my complex number z plus 1. Okay, now they're saying the argument of z plus 1 is pi by 6. That means the angle which it makes with the positive real axis is pi by 6. So this angle is pi by 6. Okay, pi by 6. And the argument of z minus 1 is 2 pi by 3. That means this is 2 pi by 3. Okay. So now our job is to show that z is equal to half 1 plus root 3i. Okay, that means I have to find the real and complex, real and imaginary part of z. So it has to be geometrically represented in this diagram. So what I'll do is I'll drop a perpendicular here. So this distance represents x and this vertical distance represents y. So I'll just remove y for a second, because right now what I'll have to do is I'll have to write the measure of this angle here. So if this is 2 pi by 3, which is 120 degrees, so this angle here is 60 degrees or pi by 3. Okay, so as of now I'll just label the points here because I'll have to represent this triangle again. So I'll label this as AOBC. Okay, so in triangle AOBC, if I draw it separately, A O ABC, sorry. So for triangle ABC, this angle is pi by 6, this angle is pi by 3. So this angle becomes 90 degrees because it's 30, 60 and 90. And this length from A to B is nothing but 1 plus 1, which is 2 units. Okay, so using basic trigonometry, what I can do is I can find the measure of side AC and CB. So uh, cos pi by 6, I can say, is AC over the hypotenuse 2, and cos 30 is root 3 by 2. So measure side AC equals root 3. So AC equals root 3, and finding BC is not important as of now, so I'll just find AC as root 3 here. Okay, now I'll draw the perpendicular here, and this length is nothing but the imaginary part y of the complex number z. Okay, I'll write z is equal to x plus iy here. Okay, now if I consider this triangle here, I'll label the triangle in blue. Okay, it's also a right angled triangle. So for this triangle, can I say sine pi by 6 is equal to y upon root 3? Yeah, because sine theta is opposite upon the hypotenuse. So sine pi by 6 is sine 30 is half. So I get the y coordinate as root 3 over 2. The y value or the imaginary part of the complex number as root 3 over 2. Okay, now with the real part. So for that, what I'll do is I'll label the point O in the diagram as well and connect it like this. So this horizontal length is the real part. Okay, and from A to O, the distance is 1 unit. Okay, so using trigonometry again, I can say cos pi by 6 equals x plus 1, which is the adjacent side, upon the hypotenuse root 3. And cos pi by 6 is root 3 by 2, which equals to x plus 1 upon root 3. Then cross multiplying, I get 3 over 2 equals x plus 1, and x equals to half. So I get my complex number z as half plus I root 3 over 2. This is what I had to prove. Coming to the B part, if w and z are two complex numbers such that modulus of z minus w equals the modulus of z plus w, show that the argument of z minus argument of w, the absolute value is pi by 2 or 3 pi by 2. Okay, so here what we'll do is we'll again start the question by representing the complex numbers w and z and minus w as well. So if I draw the Argand's plane here and label a complex number w in the first quadrant here. So minus w will point in the opposite direction with the same modulus, something like this. Okay, and if I, as of now, represent z as a complex number somewhere here. So z minus w is this complex number. This is z minus w, and z plus w is this complex number. So what they're saying is z plus w and z minus w are equal in magnitude or have the same modulus. So this is possible only if the complex number z lies along the perpendicular bisector of w and minus w. So geometrically representing it, the situation has to look somewhat like this. Just draw the axis again. So this is w and this is minus w. So this is only possible when z is pointing right like this. It's along the perpendicular bisector. So if z is along the perpendicular bisector, this distance, which is the modulus of z plus w, will be equal to the modulus of z minus w. Now we have to write conditions for the difference in the arguments of z and w. So if I'm considering the difference between argument of z and argument of w, one way is, which I can see for the first set, w and z. For this case, I can say that the difference in the argument is pi over 2. Basically, z is obtained by rotating w 90 degrees in the anti-clockwise direction. So according to this diagram, the difference in the arguments is argument of z minus argument of w is equal to pi over 2. But a different situation is also possible, in which w points in the third quadrant, something like this, and minus w points in the first quadrant. So I'll label it like this, w and minus w. And if I draw z like this, again on the perpendicular bisector, in this case the difference between argument of z and argument of w is this angle in total, which is 270 degrees or 3 pi over 2, which gives rise to the other condition that argument of z minus argument of w is equal to 3 pi over 2. Okay, so I've got my two conditions here. One is that the argument of z minus argument of w is pi by 2, and the next is argument of z minus argument of w is 3 pi by 2. And there's a modulus sign there because the difference in the arguments can be the same value but negative as well. Negative in the case when z points exactly opposite somewhere here, and in the other case as well if z points somewhere here. Okay, so we are done with this question, and then we'll continue with the next topic, which is polar form of complex numbers.